Okay, we will solve the sample problem from the book of Refrigeration and Air Conditioning from the book of Stoker. So, ito yung yung libro. Okay? So, the important thing here is how you plot in the tables. Okay? The refrigerant table or in the superheated table. So, I will show you how to plot so we can solve this problem. Okay, let me read to you. Standard vapor compression cycle developing 50 kilowatts of refrigeration using refrigerant 22 operates with condensing temperature of 35 degrees Celsius and an evaporating temperature of negative 10 degrees Celsius. So first things first for our solution. First is to draw the diagram of the refrigeration and the pH diagram. Okay, so I think this is a standard refrigeration cycle. So I will draw the 4 basic parts of refrigeration. Expansion valve, evaporator, pump, and condenser. Okay. So we all know that pump is the heart of the system. So it pumps the refrigerant. So it needs power. So we will call this the work of the compressor. So the heat will be will be absorbed in the evaporator and will be rejected into the condenser. Okay. So the standard vapor compression cycle developing 50 kilowatt of refrigeration. So that means that is a 50 kilowatt of heat. 50 kilowatts of heat. And it will be rejected through the condenser. Okay. So our working fluid or refrigerant will be R22. So we will look to the table of R22. And with the condensing temperature of 35 degrees Celsius. So our condenser has, or our high temperature side will be 35 degrees Celsius. And the evaporating temperature or the low temperature side will be negative 10 degrees Celsius. So first, calculate the refrigerating effect in kilojoules per kilogram. Okay, the refrigerating effect. The refrigerating effect can be found in the evaporator. Okay, so okay, let's solve for the refrigerating effect. But okay, we almost forgot. We need to draw the pH diagram so we can get all the enthalpy at different points. Okay, so I almost forgot this is our point 1, point 2, point 3, and point 4. So let's it doesn't matter what is the point as long as you follow the flow of direction of your system, you will arrive at the same answer. And for the pH diagram, so this is our evaporator from 4 to 1, constant pressure. Then constant entropy process for the compressor at high superheated state, and constant pressure, heat rejection, and temperature for point 2 to point 2 to point 3 by the condenser. And this is the expansion valve or the throttling process. Okay, so I will remove this. Okay. All right, so this is our pitch diagram. So we all know the temperature is 35 degrees Celsius at this point, and the evaporator is negative 10 degrees Celsius. So for the refrigerating effect, solving for the refrigerating effect, so RE can be found at the evaporator side, so we will isolate the evaporator. So isolating the evaporator, so from points 4 to 1, this is the arrow sign. I forgot the arrow sign of our direction of refrigerant. Okay, for the evaporator, so by using energy balance, okay, heat addition, so enthalpy 4 and enthalpy 1. So by using energy balance, so energy in will be equals to energy out. All the energy in, I think the energy in is only the heat addition and the enthalpy 4. Then evaporator is as an enthalpy 1 for the outward energy. Okay, so simplifying this, we got H1 minus H4. So since we have the value of specific enthalpy, okay, so we will make this specific enthalpy. Okay, notice we have H1 and H4 here. So this H1 and H4 will be the refrigerating effect as we discussed. Okay, so this is the refrigerating effect, H1 and H4. So first things first, we will find the values of H1 and H4 into our pH diagram. Okay. So solving for H1 and H4, so enthalpy, okay, this will be our enthalpy table. So H1, H2, H3, and H4. We all know that first things first, so the easiest enthalpy will be the H1. Okay. So H1. H1 can be found at saturated vapor of R22 at negative 10 degrees Celsius. Okay. So H1 can be found at negative 10 degrees Celsius. Hg, vapor, saturated vapor. So we need this data from the saturated table. That is from table A6, page 426, or in the back of the book. So negative 10 degrees Celsius. I think this is the negative 10 degrees Celsius. So saturated vapor, okay? Um, so we will, okay, this is the point. Okay, so the Hg is 401.555. Okay, so this is our Hg, 401.55. That is our H1. Okay, that is our H1, 401.555 kilojoule per kilogram. Next, okay, we have now an H1. Next is to find the H4. We already know. So check na tayo, no? We have, check na natin to. H1, check. So before we proceed on H3 or H4, so we will write the pressure. Okay, the pressure is 354.30. Okay, this is the pressure. 354. This is the pressure at 354.30 kPa. Okay. So next is to find H4. We already know H3 and H4 is constant enthalpy process. So we can easily find H3 because H3 is HF of 35 degrees Celsius saturated liquid of R22. Okay, so, okay, I will delete. We already know that H3 is equals to H4. Okay, so, and H3 is at 35 degrees Celsius HF of R22. So we will go to saturated table of R22, table A6, page 426. So that is, okay. So I will mark 35. So I cannot, ayun, hindi siya straight. Yes, I cannot straight. Don't know why. But our HF will be 243.114. Okay? 243.114. So this is it, okay? So check na natin to. We have H and H4. So we don't know the value of H2. So that is 243.114 kilojoule per kilogram. Okay, now we can solve for the refrigerating effect. So this is the refrigerating effect, okay? This notation, H1 minus H4, that is your RE. So substituting, therefore our H1 is 401.555. By substituting H1, 401.555 kilojoule per kilogram, and our H4 is 243.114. 243.114 kilojoule per kilogram. So we all know that H1 minus H4 That is our refrigerating effect. So H1 minus H4, substituting 401.555 minus 243.114. So same unit. We can arrive at the same unit. So that is what? 158.441 kilojoules per kilogram. So that is our answer for the refrigerating effect for number 1. Okay, so we can now cancel out the A. So we'll solve the A. So let's go for the letter B. The circulation rate of the refrigerant in kilograms per second. Kilograms per second means um, the mass flow rate. Okay, so we will solve for the mass flow rate, of the refrigerant. Okay, so as you see in our evaporator side, we already have a complete value of our energy equation. And notice in this equation that we do earlier, we have a given QA. We already found H1 and H4. We have one unknown value, which is the mass, and this will be the mass flow rate. Okay, so using that equation, or if you don't know what side where do you get the mass flow rate, just find the complete data of energies on this evaporating system. You can solve the mass flow rate from there. In this example, the evaporator side has a complete data because we have a given value of 50 kilowatts of heat addition. So by using this, by using this equation we composed earlier, H1 minus H4. So substituting 50 kilowatts equals to mass. Okay, class, 50 kilowatts is the equivalent of kilojoules per second. You already know that. Okay, kilowatts is kilojoules per second. Sorry. Okay, so equals to mass times. So this will become mass flow rate because we have a second time in our equation. So H1 is 401.555 minus H4. So therefore, our mass flow rate will be 0.3156. So cancel the unit of kilojoules. So kilogram per second is our unit. Okay. So this is our answer for letter B. So we can now cancel out the letter B. We have now the mass flow rate. So I think we can add this in our enthalpy table, the data of our mass flow rate. 0.3154 kilogram per second. I think we can use that in our other problem. Next will be the power required by the compressor in kilowatts. So we will find the compressor work, compressor power. Okay, so we can isolate the compressor side. Okay, so we will draw this in the other solution paper. Okay, so solving, so letter C na tayo. Okay, solving for compressor power or compressor work. okay, WC. So isolating, okay, the compressor. So from 1 to 2, okay, points for 1 to 2 work of the compressor. Since we have the enthalpy 1 or the specific enthalpy 1, but we don't have for the specific enthalpy 2, so first we will get the value of specific enthalpy number 2. The enthalpy 2, as you notice in our pH diagram, is in the superheated side. Okay, it's in the superheated side. So we will need that table A4 from page 436. Okay, so we will plot the enthalpy here because that is a superheated vapor at point 2. Okay, the problem here, so we need the values of we need the two values of axes. Okay, so first things first, so we have the entropy here. Okay, entropy, pressure, or specific volume, but I think we need the two values of that. So let's go back to our chart. So I think we can have the pressure because from point 3 to point 2, that is a constant pressure process. So what is the pressure of point 3? So let's check. At 35 degrees Celsius, the pressure is 1354.8. Pressure is 1354.8 kPa in point 3. So we can plot 1354.8. So what is the 1354.8? So this is the pressure side, okay? So maybe this is 1,200, 1,400, 1,500, 800, and 2,000 because it is divided into 5. Maybe 1,300 is between the 200 and 400, maybe in this part, okay? This is where the 1,300, what is that? 1,000. Okay, sorry. Okay. All right. Now, so we will find the 1,354 in this y-axis. Okay, this y-axis is the pressure. So, but 1,000 to 2,000 range is divided by 5 lines. 1, 2, 3, 4, 5. Okay, 1,200, 1,400, 1,600, 1,800, and 2,000. Maybe the 1,300, what is that? 1,354.8, 54, okay, 0.8 is in this line, okay? So we will draw a horizontal line. Okay, make sure that you have a straight line because make sure this is a parallel, okay? But the problem here is the table is okay. No? This is more brief of an estimation. Yes, so we have so we need one more line. Okay, so notice on the chart, point 1 to point 2 is constant entropy process. Okay, so we will need the entropy at point 1, which is in the saturated vapor state. Okay, for our enthalpy table. Um, so, so S1 is equals to Hg at a negative 10 degrees Celsius, and that will be equal to S2. So, okay, what is the value of our of S1? SG at negative 10, that is 1.76713. That is 1.76713. 1.76713 kilojoule per kilogram Kelvin. Okay, now we can plot that in table A4. So 1.767. So maybe 767, okay? So we have 1.76, 1.78. So my brief estimation in here, 1.76 is 7 is in the middle of that. So plotting. So this is the challenge here. You need to draw a straight line, okay? It must be between of 1.76 and 1.78. Okay. So I have a problem here with my pointer. Cannot be straightened. So sorry for that. It's hard to make a straight line using this. Okay. So okay. So I think okay, this is our line. Okay, so the cross section of this will be our enthalpy at x-axis. Okay, enthalpy at x-axis. So the crossover point is this. Okay, this is the crossover point, and we will draw an vertical line. So I think the vertical line yes, it is the straightly the horizontal line. Okay, since I cannot yon. Okay, all right. Um, so plotting into the our enthalpy. So that is 400, estimated 435. Okay, 435 kilojoules per kilogram. That will be our H2 at superheated side. So, okay, let's write that in our list. 435 kilojoules per kilogram. Okay, so now we have a complete value. We have H2, H1, and so now we can find with the work of the compressor. So by energy balance, sorry, energy in is equals to energy out. All the energy in is work of the compressor, and the H1 is equals to H2. Okay, so simplifying, H1 minus, sorry, H2 minus H1. Okay, so big letter. So we will convert this into specific. Okay, specific enthalpy. H2 minus H1. So therefore, substituting for the compressor, our mass or the mass flow rate is is what? 0.3154. 0.3154 kilogram per second. H2 is 435 kilojoule per kilogram minus H1 401.55 since kilojoule per kilogram. Okay, so the work of the compressor is, so what is the compressor? That is 10.54. Okay, 55 na lang. Okay, kilogram per second. Okay, so cancel si kilogram, no? Ay, sorry, that is kilojoule per second, or this is 10.55 kilowatts. Okay, that is the work of the compressor. So we already solved letter C, so we can now cancel out letter C from our equation. So next is the coefficient of performance. Okay, solving for the coefficient of performance. So already know COP is the ratio of your heat to your compressor work. So the performance will be substituting QA. QA is given 50 kilowatts all over 10.55 kilowatts. So our COP is 4.76. So that is our COP. Next is to solve for letter E. So letter E is the volume flow rate measured at the compressor suction. So we already know that 0.122 is the compressor. So the inlet of the compressor is the compressor suction. So that is 0.1, okay? Or 0.1 here in our pH diagram. And we will solve for the volume flow rate, okay? Volume flow rate at 0.1. Okay, since 0.1 is in saturated vapor, so we will use VG at 0.1, which is VG at negative 10 degrees Celsius. So by looking at our chart, saturation chart, table A6, so VG is 65.339. So, but be careful, the unit here in our book is in liters per kilogram. So we will convert this into SI unit, which is meter cube per kilogram. Okay, 65.3399. So VG at 0.1 is 65.3399 liter per kilogram. Okay, this is the specific volume. So we will convert. So for every 1 liter, for every meter cube, there is 1,000 liter. So our VG will be 0.00, okay, 1, 2, 3. So 1, 2, 3, only 0.0653399 meter cube per kilogram. Okay, so moving on. So we can get the volume flow rate of that. So volume flow rate, by unit analysis, we can use the mass flow rate. Okay. So if we multiply this by mass flow rate, which is, what is our mass flow rate again? 0.3154. 0.3154 kilogram per second. So we can now cancel out kilograms, and the unit will be meter cube per second. So our volume flow rate at compressor suction or at point 1 will be, what is this? It is 0.0206 meter cube for per second. Okay, so this is our answer for letter E. Okay. Or if you want the English unit, so we will convert this to liters. Okay, so that will be, so 1, 2, 3, so 20.6 liter per second. Okay. So we already solved the letter E. The last is, sorry, we have the letter F, the power per kilowatt of refrigeration. So the power of kilowatt of refrigeration, we already know that that is the reciprocal of COP. Okay, because COP is the power of the compressor that drives the heat, this heat. For the power of kilowatt per refrigeration, that is the reciprocal only of the COP. Okay. So solving for the power per kilowatt of refrigeration, power per kilowatt, so that will be, or the power of refrigeration, that is work of the compressor all over the heat addition, or simply the reciprocal of COP. Our work of the compressor is 10.55 kilowatts all over the heat addition, which is the given, 50 kilowatts. So the answer is 0.21 kilowatts per kilowatt. So this is the unit for the power of refrigeration. Okay. So lastly, letter G. Okay. For our G, the compressor discharge temperature. Compressor discharge temperature, or the discharge of temperature is at point 2, so we need to find P2. So in this point, the temperature discharge of the compressor itself. The temperature, discharge temperature, can be seen on TS diagram. So we will convert this page diagram into TS diagram. Okay, so this is point 1. And point 2, a constant entropy, raising temperature at constant entropy, raising pressure. And the condenser, point 3, expansion valve 3 to 4 at constant enthalpy. So this is a constant enthalpy curve. And evaporator. So this P2 is called the compressor discharge temperature. See the table A4 again, that R22 of superheated state. So as you see, we have the temperature below. The temperature, this is the curve of the temperature, okay? Negative 30, 20, negative 10, 0, 10, 20, so on and so forth. So this is the curve of 50, okay? This is the curve of 50, and this is the curve of 60, okay? 40, 50. Okay, so we will follow the curve of this intersection. So we will follow down the curve. So this is an estimation. So I think this is around the 55. Yes, approximately 55 degrees Celsius. So this is the temperature discharge of the compressor. Around 55, or estimated 55 degrees Celsius. So much better you can use the AutoCAD software, so you can be accurate when reading those charts. Okay, so thank you, and that's all.